Okay.
Yes.
Do you?
Yes,
Okay,
it's perfect.
Okay, so hello everyone, and thank you for having me here. So, as already said, I've just finished my PhD in Bocconi, and I've just started a postdoc in Paris, and I'm going to tell you about this recent work. I'll start with an introduction about the statistical physics approach to the study of generative diffusion. And then I'm going to tell you about the theory of speciation transitions in diffusion model with general class structure, which is a work I have done in collaboration with Marco Benedetti, Giulio Biroli, and Marc Mézard. Okay, so let's start with the introduction and let's start talking about diffusion models. So diffusion models have established themselves in recent years as the state of the art for image and video generation. And let's see how they work. So we start from some data that in a high dimensional space Rn. And we assume that these data are distributed according to some target probability distribution that we call P0. So the goal of generative diffusion is to sample new data from the target distribution. And we can take, for example, images. The way diffusion model works is by progressively adding noise to a sample data point according to the forward process described by the stochastic differential equation written above, where dw is just Brownian motion. And we go on with this process until we reach a completely random state. So now one would like to be able to take time backward and inputting a completely random state to the model, be able to reverse this process and obtain a sample from the target distribution. So can we do this? Yes, provided that in the reverse process or in the backward process, we add the correct drift term to the stochastic differential equation, which is the term highlighted here. So the gradient of the logarithm of the probability density at time t, also known as the score function. And if we do this correctly, there is a theorem that guarantees that these two processes generate data according to the same probability density. So in recent years, there has been a line of research devolved into studying generative diffusion with statistical physics tools, mainly because this model naturally live in a high-dimensional setting that can be well analyzed through statistical physics, and they are prone to symmetry breaking and events and phase transitions that can be well uncovered with tools from statistical physics. In particular, I'll introduce a recent paper known as titled Dynamical Regimes of Diffusion Models, where indeed we can describe in the backward process some dynamical regimes. So starting from a large time, capital T, we are inputting the model completely a Gaussian state, and we want to reproduce a target distribution, which here is composed of two classes of images. So what happens is that starting the backward process at large time, at the beginning, the trajectories are purely Brownian. Only after we cross this first transition known as the speciation transition or speciation time, each trajectory will commit to a single class of data. So after we pass speciation, the fate of the trajectory in terms of class is sealed. They won't change it anymore. And we also know that diffusion models are prone to what is known as memorization. So instead of generating new data, which is the desired behavior, they can indeed reproduce data from the training set. But they've shown that this memorization time, this memorization effect only happens after a certain memorization time, so after which we have the collapse of the trajectories onto single data points. So it is clear that the interesting region is the green one highlighted here, and we would like, first of all, to study where it starts. So how can we compute the speciation time? Always in this work, they have started this process of characterizing speciation time by studying a simple model. So as a target, we can consider a mixture of two well-separated Gaussians. So here I write for reference the distribution at time t. And what do I mean with well separated? That the first moments of these of our two Gaussians, the distance between the two first moments scales with the system size n. So to see when speciation happens, one can project the trajectory onto the vector that connects the two means, obtaining an overlap quantity. And for this overlap, the backward stochastic differential equation has a closed form. So everything depends on this diffusive potential U that has this change of shape with time. So in particular, starting at large time with the yellow curve, you see that it has a single well structure, while going towards a smaller time, it develops a double well structure. And the time at which this symmetry breaking takes place is precisely the speciation time. So they found that speciation scales logarithmically with the system size n with a prefactor of 1/2. And we can generalize this a little bit when instead of having access to the full target distribution, we have only some samples from it. So we have a covariance matrix of the samples. And the general version of this criterion considers lambda as this quantity lambda, which is the eigenvector of the first principal components. But you can see that, again, speciation scales logarithmically with the system size. The main limitation of this criterion for speciation is that it only applies when the classes of our target distribution have a separation of first moments. But we know that this is not the only case. So what happens when there is no separation of the means of the different classes? And images are a good example of this because the differences of different classes of images are encoded more into higher moments than into the means. So if we start the backward process from a completely random state, we have seen that the speciation is indeed the time at which trajectory commit to a class, but we can also look at it into the forward process direction, and saying that it is the time at which trajectory become merged. So it is the time at which if we have a classifier, it can start committing some errors when attributing a trajectory to a class, to the class it originated from. So we can characterize speciation with this misattribution notion. And this is precisely what we have done in this work, the theory of speciation transition in diffusion model with general class structure. So let's be a little bit more precise. And we start from a target distribution, which is a mixture of different classes, so a weighted sum of different components that are indexed here with the letter R. And we can assign a sample from this distribution to a component by computing the Bayesian classifier and then assigning it to the argmax of these probabilities. But there is a problem, of course, because this decomposition is in principle not unique. Indeed, if we have a distribution like this, for example, we could consider it of being made of 2 classes or 4 different ones. So to address this problem, we have introduced what we call a proper density decomposition. So the idea that if we take a sample from one component, a component R, in high dimensions, that it will be classified correctly with high probability, even after we add to it a small but finite Gaussian noise. So let's be again a little bit more precise. If we sample AR from the component R of the mixture and we corrupt it with some Gaussian noise to obtain A tilde, then we want for our distribution that the probability of assigning A tilde to a different component, so S different from R, is vanishing for n that goes to infinity. And this is a definition of what we call the proper density decomposition. So it is clear that this is a form of a concentration property. So we can think about it as coming from a large deviation form of the distributions of every component. And we can write each component with this exponential form, with this function f being just the log density. So if we rewrite the condition for a proper density decomposition with this formalism, what we see is that we are asking actually that the correct component is exponentially dominant with respect to all the other one. So this is what we need from our target distribution. Moreover, if this f function have a property of self-averageness, so if they themselves concentrate towards the mean, then we call our proper density decomposition a pure density decomposition. And we can write it with this double index notation, meaning that we are taking the average of the logarithm of component S over the statistics of the samples coming from component R. And the intuition for the pure density decomposition is that since this self-averaging does not hold when the components can be further decomposed, it is a signature of a minimal proper density decomposition. So now that we have carefully described what we want from our target distribution, we can finally move to the diffusive process. So let's add the diffusive noise. And we are considering a typical trajectory x of t, which is the forward process evolved version of one sample A from the target. Then each component will evolve with time, will be given by the convolution of the original component with a Gaussian diffusive kernel. So this as the form of a disordered partition function with an external field x. And so we can, so it describes an effective free entropy density with these functions f rs of t. So let's look at what happens during the diffusion process. We have a sketch of the two components, PR and PS, and a sample A from PR. Then above there is written the condition for the decomposition to be pure. Once we add noise, you can see that indeed the two components are closer together, but they are still well distinguishable until at some time they are actually merged. And when does this happen? As you see written here above, merging between components happens when the difference between the average free entropies becomes comparable with their fluctuations. And this is precisely how we characterize the speciation time in what we have called the general criterion, which is written here. So let's recap and look at each term carefully. On the right-hand side, we have the difference between the average free entropies of the two different components R and S when the sample originally comes from a component R. And on the right-hand side, we have the fluctuations, which is computed as the square root of the variance of the log densities. And K is just a constant that takes into account, for example, the threshold of misattribution that we are willing to consider. Once we have described this general criterion for speciation, we can derive from it the scaling of speciation time. Speciation times, I should say. Indeed, since we know that speciation happens at large time, we can perform a large time expansion, which amounts into approximating each component of the mixture with a Gaussian. And what we found is that in the case in which there is a separation between the first moments of the components, this is the scaling that we obtain for the speciation time. So there is a main part, which is 1/2 log n, that perfectly recovers the previous scaling that we have seen before. And then there is another term, which depends on this function ARS, which is a simple function of the difference between the two first moments of our components. And finally, a finite shift depends from a constant, the arbitrary constant k. While when there is no separation between the first moments of the components we are considering, the speciation time has this scaling, which is again mainly it scales with the logarithm of n, just with a different prefactor, 1/4 instead of 1/2. And of course, the terms that takes into account the specific components we are considering is a function of their second moments and not their means. So we wanted to test a little bit this new case that we have analyzed, that we have analyzed asymptotically. And to do this, we have chosen a simple case, which is a Gaussian mixture. This time, of course, we take a mixture of Gaussians with zero means and different isotropic variances. So this is the form of the distribution at time t. And indeed, we know that in high dimensions, this distribution will concentrate into thin shells of radii, which is proportional to the isotropic variance. So we have a pure density decomposition because we can really distinguish the two components, just not through their first moment. So we can compute explicitly both sides of the general criterion for this simple model, and here I put the expressions just to show that it's doable. And actually, we can even write a backward equation for a radial parameter in closed form. So we can use again the previous criterion to define speciation, the one that looks at the change in shape of the diffusive potential. And what we find with these two methods, so the previous criterion based on the potential and our new general criterion, is a confirmation of the asymptotic scaling of 1/4 log n. So this is already a nice result, but we wanted to go a little bit further and to analyze a case which is more structured. So we chose to study a mixture of one-dimensional Ising model. So the Ising model is, of course, a model of ferromagnetism where we take n sites and we assign spin variables to it that interact with each other with the Ising Hamiltonian. This model is indeed structured because there are correlations, and these correlations depend from the inverse temperature that we are considering through the parameters that we call correlation length. Indeed, here, for example, I plot two Ising chains at different inverse temperature. And one can convince, we can convince ourselves that they are these. If these are the components of our mixture, they will be picked into a different region of the configuration space, even though the mean of each component will be 0. So this is precisely the target distribution that we study. A mixture of one-dimensional Ising models at different inverse temperatures beta r. And for this for this model, we cannot derive speciation explicitly from the potential criterion. And as we have already said, the components cannot be distinguished by their first moments because the first moments are identically 0. So we are precisely in the case where we need the new general criterion. So to apply it, one can see that have a look at the time evolved components during the diffusive process. And as we have already noticed, they will resemble a partition function, in this case the partition function of one-dimensional Ising model, but with an external random field given by the with an external random field x of t. So this in the literature is known as a random field Ising model. And we were able to use some results that allowed us to compute an exact expression for the average free entropies through replica computation. So we have an exact analytical expression for the left-hand side of our general criterion. Instead, for the right-hand side, for the terms that takes into account the fluctuations, the variance, we don't have an exact expression. We can only approximate it with its large time expression. And so this is what the general criterion looks like, with an approximation, the approximated variance on the right, and an exact analytical function on the left. But we didn't want to lose completely the dependence from the specific components RS. So we had retained this function CRS, and for this model we can we can obtain an asymptotic exact closed form expression for this function CRS. So this allows us to have an estimate of speciation times for an analytical estimate of speciation times, and we would like to, of course, compare it with some numerical experiments. Indeed, one can compute the exact score function using a transfer matrix method numerically, and we can use it to integrate numerically the backward process of the diffusion model. And we perform what are called U-turn experiments. So we start the diffusion, we start from a configuration and we run the forward diffusion until a certain point, which doesn't need to be large. Then we stop, and from that point we run the backward process. Then we compute the attribution, the Bayesian attribution to each component, and in particular we can compute the misattribution fraction. And we repeat this for different U-turn times. So I'll show you the results first for a mixture of just two Ising models. So in this plot, what I'm showing are with solid lines, we have the average free entropy differences between the two components at different times for different number of spins, but the curves are all collapsed and they perfectly match the analytical version. With the colored area, we are showing the standard deviation, so the fluctuation terms for the obtained numerically. And with the dashed lines, the misattribution fraction computed at different U-turn times, as I was describing before. So the first thing that we can notice is that when the fluctuations are of the same order as the average free entropy difference, so when a colored area, let's say, reaches 0, the corresponding color, the curve of the corresponding color of the misattribution fraction starts to rise. So this is a confirmation that our criterion indeed captures the correct phenomenon. And finally, with the colored ticks on the x-axis, I have marked the speciation times that we could predict analytically with our criterion, and you can see that again there is a close match to when misattribution starts to rise. We can go a little bit further and consider more components. So here, for example, we are considering a mixture of three Ising models at different inverse temperatures. And in this case, we can compute attribution matrices between the different components, again, for different U-turn times. And so what I wanted to tell you is that our criterion allows us to take into account multiple speciation events, because as you see here, T1 and T2 are the speciation times computed analytically again, and they take into account the mixture of the merging time of the first two components, the one that are closer in terms of inverse temperature, and only after the second speciation time all components start to be merged. So a very quick summary, we have seen a criterion for the speciation transition that holds for a general class structure, because we have only defined some general properties of the target distribution that we need to apply this. And this criterion nicely confirms a previous scaling of speciation time, and it extends this analysis to new cases. Thank you very much.
Thank you, Beatrice, for the presentation. And please, if there are questions, you can ask. I don't see questions, but which are the future direction of your research, Beatrice?
Of this work in particular,
Yes.
so the analysis that was done by takes into account for now not only first moments but second moment separation. It would be nice to extend it maybe to consider general, let's say, moment separation, but it is for sure a more complex case that we need to understand how to treat. So this could already be something. This is something that we are looking into. Yeah, primarily I would say this point.